Friends, welcome to the tutorial series on Basic Electrical Engineering Made Simple. In this tutorial, we shall discuss about the passive circuit elements. During the process, we shall define resistance, inductance, and capacitance circuit elements and describe each element in terms of circuit viewpoint, energy viewpoint, and physical viewpoint. Also, we shall bring out the concept of electromagnetic field and electrostatic field. Friends, during the earlier tutorial, we have discussed in detail about the resistance circuit element. Therefore, during this tutorial, we shall just revise in brief. Friends, we know that the passive circuit elements are those which can receive energy, and the energy received is either absorbed and converted into heat or light, or it can be stored in the form of electromagnetic field or electrostatic field. Here are three circuit elements: resistance, inductance, and capacitance. Note that the resistance is connected across the DC source, whereas inductance and capacitances are connected across the AC source. We learn more about this as we proceed further. First, let us consider the resistance circuit element. We know that the resistance is a property of circuit element which opposes the flow of current. The energy received by the resistance is converted into heat in iron box and is converted into light in electrical bulbs that you know. Friends, first let us consider the resistance in circuit viewpoint. And here is a circuit wherein a voltage of V volts is directly connected across the resistance R ohms. And you know the current is flowing away from the positive terminal of the source, and Ohm's law states that the current flowing through the resistance is directly proportional to the voltage across it, provided the temperature remains constant. Hence, I is proportional to V, and I is equal to V divided by R. Note that R is in the denominator because the resistance property opposes the flow of current. Using I is equal to V by R, we can have another two equations as indicated here. Friends, next we shall discuss about the resistance in energy viewpoint. The three equations which we have obtained using Ohm's law are listed here. We know that power is equal to V into I watts. By substituting V is equal to I into R, we get P is equal to I squared R watts. And by substituting I is equal to V by R, we get P is equal to V squared by R watts. Friends, we know that physically the resistance is a metallic wire of certain length, say L meters, and the area of cross section of the wire, say A meter square. We also know that the resistance is directly proportional to the length of the wire L and inversely proportional to the area of cross section of the wire. So, resistance R is equal to rho into L by A, where rho is the specific resistance of the material in ohm meter. Since the energy received by the resistance is converted into heat or light, for safe working of the resistance, the energy received has to be dissipated. Hence, the resistance wire has to be embedded by coating of acrylic, alkyd, epoxy, or polyurethane made up of one or more layers of polymer resins joined by urethane links. Friends, here you find some of the fixed resistors and the variable resistors. You also find that the resistor with heat sink because the power is to be dissipated large in this resistance. This resistance is called as a rheostat and this resistance is called as a potentiometer that you know. Friends, usually the color code is printed on the surface of the low power resistors as shown. We have to read the color code and find the value of the resistor. The leftmost digit is a number, the next digit also is a number, and the third or the last digit is a multiplier. To the extreme right, you find the tolerance. Gold is plus or minus 5% tolerance, silver is plus or minus 10% tolerance, and if there is no color, the resistance will be of 20% tolerance. So using this format, we find that the resistance value shown is 230K having tolerance of plus or minus 10%. Friends, next we shall take up the inductance circuit element. Inductance is that property of a circuit element which opposes the rate of change of current. Note, the resistance property will oppose the current, whereas the inductance property will oppose the change in current. Hence, inductance is known as current sensitive element. Friends, to understand the concept of inductance and induced EMF in it, we need to discuss the Faradays experiments. Here is a circuit in which a current sensing galvanometer is connected across a coil of N turns and there is a permanent bar magnet. If the magnet is stationary as shown in this figure, there is no deflection in the galvanometer, meaning there is no current flow in the coil and there is no EMF induced in the coil. But when the magnet is moved towards the coil, the deflection is found to be on the right side as shown here. What does this mean? The current in the coil is produced due to induced EMF in the direction as shown. If the magnet was moved away from the coil, the deflection was found on the left side as shown. The current was found to be reversed. Further, it is found that the deflection was more if the velocity of the motion of the magnet was increased. If the number of turns was increased, EMF also was found to increase. The conclusion is EMF depends on the rate of change of current, that is di by dt. The induced EMF also is dependent on the flux linkage and the flux linkage is equal to N into phi Weber turns. EMF induced is proportional to the relative motion between the coil and the magnet, meaning either the coil can be kept stationary and the magnet is moved, or the magnet can be kept stationary and the coil can move, the result will be same. Since EL is proportional to di by dt, we can write EL is equal to L into di by dt, where L, the proportionality constant, is called as inductance and its unit is Henry. From the equation of EL, we see that L is equal to EL divided by di by dt, meaning inductance property will oppose the change in current. Friends, during the Faraday's experiment, we found that the direction of the current in the coil depends upon the motion of the magnet or the coil. So, to find the direction of the field produced, the right hand grip rule is used. It states that grip the coil by bending your four fingers of the right hand and hold the thumb straight as shown. Then bent fingers point towards the direction of the current in the coil and the straight thumb points to the north pole of the field. Look at the figure which we discussed earlier. When the north pole of the magnet is moved towards the coil, the current is found to flow as shown. If we apply the grip rule, you find that the north pole of the field produced is on the left side as shown. What does this mean? You are trying to move the north pole towards the coil, but the magnetic field produced will try to produce repelling force. Friends, this is the Lenz's law. You know, the Lenz's law states that the EMF induced in the coil will oppose the cause. The cause that produces the induced EMF in this coil is the motion of the magnet. Hope you understand it. Now, you can think what happens if the north pole of the magnet is moved away from the coil, the direction of the current in the coil will be reversed. So, south pole of the field is produced on the left side and you are moving the north pole away. The field is trying to attract by producing the south pole. Is it not interesting? So, here is a circuit wherein AC source of V volts is connected across an inductance of L henries. Let I be the current flowing through it. Since the source is alternating, current flowing through the inductance also is alternating and is changing with respect to time. So, as we have seen earlier, EL is proportional to di by dt and EL is equal to L into di by dt and hence L is equal to EL divided by di by dt. That is so simple. Friends, now let us see the inductance circuit element in energy viewpoint. We know that the instantaneous energy E is equal to VL into IL into dt, where VL is the voltage across the inductance and IL is the current flowing through it. Hence, by integrating it, we get E is equal to integration of VL into IL into dt. But we know VL is equal to L into di, L by dt. Therefore, E is equal to half into L into IL square joules when L is in henries and IL is in amperes. Friends, physically, inductance is a wire of N turns wound on a former as shown, where L is the length of the former in meters and A is the area of cross section of the former in meter square. Note, L and A are not the dimensions of the wire as in resistance. This is very important. Inductance also is defined as the flux linkage per ampere, where N into phi is the flux linking the coil in Weber turns and I is the current in amperes. But we know flux phi is equal to mmf upon reluctance and mmf is equal to N into I ampere turns. Reluctance R is equal to L divided by mu naught into mu R into A. By substituting for mmf and reluctance and solving, we get inductance L is equal to N squared mu naught mu R into A divided by L, where Mu naught into mu r is the permeability of the medium on which the coil is wound. Mu naught is the permeability of the free space and is equal to 4 pi into 10 to the power of minus 7 henries per meter. Friends, here you find different types of inductors. You find ring type core on which the wire is wound, and you find inductors wound on different types of cores. Here is an air core inductor. Air also can be used as a core. If the core is other than air, the inductance value will be much more than that of air core inductor depending on the value of mu. Friends, next we shall take up capacitance circuit element. You know that the capacitance is that part of a circuit element which opposes the rate of change of voltage across it. It exhibits its property only when the voltage across it is changing. The energy received by the capacitance is stored in the form of electrostatic field. Hence, the capacitance can be called as a voltage sensitive element. Next, we shall take up the capacitance circuit element in circuit viewpoint. Here is a circuit wherein an alternating source voltage of 5 volts is connected across a capacitance of C farads. Since the source voltage V is alternating, the voltage across the capacitance also is alternating. Let Vc be the voltage across the capacitance. We know that the current flowing through the capacitance Ic is proportional to dVc by dt, and hence Ic is equal to C into dVc by dt, where the proportionality constant C is called as the capacitance and its unit is farads. Therefore, C is equal to Ic divided by dVc by dt. So, you find that dVc by dt is in the denominator, and hence the capacitance property opposes the change in voltage. Therefore, capacitance is a voltage sensitive element. Friends, instantaneous energy stored in the capacitance E is equal to Vc into Ic into dt. By integrating, we get E is equal to integration of Vc into Ic into dt. But Ic is equal to C into dVc by dt. By substituting and solving, we get energy E is equal to half into C into Vc square joules when C is in farads and Vc is in volts. Friends, physically the capacitance is made up of two conducting plates in between which the dielectric material is placed as shown in figure. The conducting plates could be of silver, aluminium or copper. The dielectric material could be of air, aluminium oxide, glass, mica, paper and so on. The capacitance of a parallel plate capacitor is found to be directly proportional to the area of the plates where A is in meter square and inversely proportional to the distance d meters between the plates as shown. Hence, C is proportional to A and C also is proportional to 1 upon d. Therefore, C is equal to epsilon R into A divided by D farads, where epsilon R is called as the permittivity of the dielectric material. Also, epsilon R is equal to epsilon naught into epsilon r, where epsilon naught is equal to 8.854 into 10 to the power of minus 12 farads per meter. And epsilon r is called as the relative permittivity and is defined as the ratio of permittivity of the medium to the permittivity of the free space. Friends, here you find different types of capacitors of different sizes and shapes wherein different dielectrics are used. You also find air dielectric capacitors which are variable capacitors. Friends, now let us summarize what we have learned in this tutorial. Passive circuit elements receive energy. Important passive circuit elements are resistance, inductance, and capacitance. Resistance opposes the current, inductance opposes the change in current, and the capacitance opposes the change in voltage. Resistance absorbs energy, inductance stores energy received in the form of electromagnetic field, and the capacitance stores the energy received in the form of electrostatic field. Inductance is a current sensitive element and the capacitance is a voltage sensitive element. Physically, resistance R is equal to rho into L by A ohm. Inductance L is equal to N squared mu naught into mu R into A divided by L henries, and C is equal to epsilon A divided by D farads. Friends, I hope you enjoyed this presentation on passive circuit elements. If you have any suggestions and clarifications, please forward it to my email. Thank you for watching this video.